Hello, everyone. So today I'm going to be talking about how we handle Booleans in Dyalog APL. I hope you had your coffee. So you should know that Booleans are the integers 0 and 1. APL uses Dyalog APL, and many other APLs use a particularly unique and exotic way of storing Booleans, which is to write them all to memory in order. Other languages, because they can't take advantage of arrays as much, almost always use an entire byte for a Boolean. And this makes some things easier because reading one particular bit out of a byte is harder than reading just the whole byte on any modern architecture. But it makes Dyalog APL, when we use these bit Booleans, much faster. The reason for this is that the time it takes to do an operation, provided it's well implemented, is almost always related to the amount of data that you have to write during that operation. So when Dyalog APL does a primitive with a Boolean result, it's 8 times faster often than it would be if it just had a short integer result. So I'm going to give an example of, in Dyalog APL, what Booleans can do for us from a performance standpoint. The problem is that you have a string, a file, and some Windows programmer has gotten at it, and they've put some CRLFs in your file. Maybe they haven't even put them in the whole file if they're a really awful Windows programmer. And so I have on the left a solution that a C programmer would call simple, and on the right a solution that an APL programmer would call simple. The C solution, it loops over the source string, copying it to the destination string, except whenever it sees an LF, if the last character was a CR, it backs up the pointer by 1 so that LF overwrites the previous CR. The APL solution, it just retains every character that's either not a CR or doesn't come after an LF. So this solution will actually be, if there's a CR at the end and an LF at the beginning, it will remove that, but it's easy enough to fix that with a with 1 comma swap minus 1 drop, and that doesn't really impact the performance. So here is how the C solution performs. I have here a log-log graph of the length of the string you're applying to, and the speed, the amount of data that you can write in megabytes per second. So the C solution is running at maybe 1.4 gigabytes per second for the large strings. And this is pretty good. For context, the fastest that this machine can write data, period, is 11 gigabytes per second. So it's not perfect, but very fast. There's actually an optimization that I can make to the C solution, and that's if you look at this if statement here, typically when you're programming in C, if statements like this, they actually do compile to branches in the processor, and in order to execute branches quickly, the processor has to predict what the result's going to be. So if it can't predict the result, it's often slow. And the optimization is to instead of conditionally subtracting 1 from dest, just instead subtract that Boolean value. So here's what happens when you apply that. Well, it's slower. And yeah, so the reason for this is actually an optimization, I promise. The reason is that I've been very generous with the strings that I've given. And I think this would be something that you typically see in a file, but if you're doing a different sort of string replacement, maybe not. So I've only put 1 CR-LF per 100 characters, and I haven't put any CRs that aren't followed by LFs or LFs that aren't preceded by CRs. So that means that this C solution that actually uses a branch can go much faster because it just predicts, well, there's probably not a CR-LF there. And all but 1/100th of the time, it's correct. And actually, it gets very lucky at the beginning here. I think what happens is that there are, in my test data, there are actually not any CRLFs in the 100 or 300 item string, and that means it just always predicts perfectly. So yeah, it's very good at guessing when it's already seen what happens. Now here's Dyalog 16. This is very good. Dyalog 16 is somewhere around half as fast as C. Most interpreted languages can't come anywhere close to this. So Dyalog's own regex implementation, which is a pretty fast regex implementation that's also used by some other languages, comes in at 200 megabytes per second, right around the bottom of this graph. If I put Python in, you would not see it. I believe Python is actually below the floor here, unless you're using regex, when again, it'll come in at about 200 megabytes per second. So, so in terms of interpreted languages, this is really a very good performance. However, in Dyalog 17, what I've done is, well, in 16, one of the limiting factors on this algorithm is actually the performance of equality testing. Dyalog has had actually pretty slow equality and various comparisons for a while. So in Dyalog 17, I used vector instructions, which are very good at doing these equality operations on many items at once. And so with SSE2, the comparisons are actually up to 8 times faster, usually 6 to 8 times faster. And with AVX2, they're up to 16 times faster. So here's Dyalog 17. It's faster than C. And yeah, so in fact, this is, for large strings, this is faster than C. For small strings, Dyalog has array overhead, which someday I'd like to address. There are ways to do that, but it's pretty difficult. But now our limiting factor is actually the implementation of compress. And I took a look at compress. Here it does well, but part of the problem is that it's also using branch prediction. So like this first C solution, when we have a different string that's not so predictable, it will start to get slower. And so I looked at this, and I looked at what vector instructions I had available, and I looked again in disbelief, because there were not many vector instructions available for this, but eventually I found something. And this is a prototype now because it's not implemented for every architecture. I don't have the checking whether the instruction set's available and that stuff. But it'll probably make it into 17.0. And so here is what we can do with an improved compress. So this is over twice as fast as C, and it's consistently that fast. So this orange C solution is sort of cheating, and the purple APL solution does not cheat at all. So it's if you're really comparing it to the solution that is the same, it's almost 3 times as fast as C for large arrays. So the reason that APL can do this, well, you say, why can't C do this? APL is written in C. What's the deal? Well, part of the issue is that APL is not actually written in standard C. It uses vector intrinsics to call vector instructions. And we do this, and we go through all this hassle to make sure that these vector instructions are actually available, and we code different instructions on different architectures and things like that. In standard C, you can't, well, you have to use extensions to the compiler to do that, and then you'd have to write the same algorithm multiple times for different architectures. And if you ran into an architecture you didn't know about, it just wouldn't work. You'd have to have a fallback if you don't have all those available. So you can't do what we do in APL in C easily. I mean, we can't do it easily, but we did do it. And also, the problem is that the compiler, this code is much harder for a compiler to understand than this code is for our interpreter or even our compiler to understand, or if we had a compiler. And so, yeah, I mean, this is implicitly using this sort of compress pattern, where you're only copying elements if a certain condition holds. And you can try all sorts of permutations on this, and in no instance on any compiler will it ever vectorize. There's just no compiler that knows how to do a compress. But even if the compiler implementer implemented a compress, they would have to figure out that this code is saying that you want to do a compress. And that's very difficult. Whereas in APL, we have to write a good compress algorithm, which is difficult. But then once we do that, it'll work every time you use a compress. So the APL statement really kind of says what you actually mean, and that makes it much easier to implement. But the other big factor is, as I said, Booleans. So a lot of the reason that this solution is so fast is that the results of both these comparisons are Booleans, which take very little space in memory because they're only using 1 bit per bit. So this rotate operation and this OR are essentially free. And actually, the comparisons can be much faster because they don't have to write entire integers as well. So using Booleans for these intermediate values means that APL can do all sorts of complicated manipulation of, I mean, I chose this problem because it was simple, but there are many more complicated things that we can do. And C still can't do those, of course. So using Booleans is really a big improvement. But to get all that improvement, you do need fast Boolean algorithms. So now I'm going to talk about one of the things that I spent a lot of work on in version 16, which is Boolean Transpose. So when Dyalog APL was first created in 1982, the developers did not have the time, the machines did not have the disk space to have a different algorithm for transposing every type. So instead, the way it was done is they had a function to read a bit from an array, and they would initialize on the type, and it would put that function pointer somewhere. And so they'd call this function and read a bit from the argument, and actually you can optimize it so that you go across the left argument all in order. So they would read a bit, accumulate it, read a different bit somewhere else, accumulate it, and so on. And this is very inefficient because you have to do a full bit read and then actually also a shift, which is expensive on x86 for historical reasons. So the full byte read and a shift for every bit you want to write in the result. So it's much better to go a byte at a time. And JFode here did actually find a solution that does this, but only for matrices where both the rows and columns where the number of rows is a multiple of 8 and the number of columns is a multiple of 8. But, I mean, that gets you a 64th of matrices. And these Dyalog APL programmers, they all use these matrices with weird shapes like 10 by 10 or something. So in fact, I was able to, for Dyalog 16, make our transpose fast on all matrices. And the way I did this was by splitting it up into a large number of cases, as shown here. This diagram is a bit tricky to understand at first, but it's very helpful to think about transpose. The way this works is that I have one pixel block for each size of matrix, and the colors show what cases they fit into. So at the top left here, the very top left pixel is a 0 by 0 matrix, and going top right here is a 0 by 0 matrix, and going left from that, you have then 0 by 1, 0 by 2, and so on. And going down, you'll have 1 by n, 2 by n. So now the cases here, this blue at the top and the left is, those are the trivial cases. Those are the cases where you don't actually have to do anything. Transposing a 0 by n, an n by 0 matrix. Obviously, there's no data to transpose. You just write the shape and then you're done. Transposing a 1 by n matrix, the data will still be in the same order. So maybe you have to create a new matrix so that you can change the shape. but then you just copy the data over directly, which is very fast. So these are, it's always a nice optimization when you get to do nothing. But Dyalog 15 didn't actually do nothing. So now it does. That's nice. And then this, all these greenish things, I know they're hard to tell apart, and that's because I'm not actually going to talk about the differences. These are what I call bit interleaving, which I'll get to on the next slide. Then in these bright red bars, these are my extension of Jay's algorithm to do an 8x8 transpose. I was able to extend it to work on when just the columns just the column length, number of columns, row length, is a multiple of 8. And then when we have a large matrix that doesn't have that, we actually do an overtake on the last axis before transposing. So yeah, that's all our cases. Bit interleaving is one of the major things that I did for version 16. It's actually very widely applicable. The idea is that given a register containing some number of bits, L bits I have, you'll insert zeros in between these bits in a regular pattern. So you'll interleave it. You have in bits, then im zeros, then in bits, then im zeros. And there's in BMI2, which is available on x86 processors starting in 2013, there's an instruction which basically does expand on Booleans. And that makes this very easy. But there's also a more complicated method using some pre-computation that works for that without too much slowdown. And this is useful for a lot of things. In version 16, it's used for overtake on Booleans, for catenate on the last axis of two Boolean arrays, and for transpose. And in version 17, it will also be used for replicate of a Boolean vector by a small constant value. So yeah, that's all I'll say about that. That is, or no, I'll say. So if we have, for example, if we have one of these matrices here, that's a matrix with few rows and a lot of columns. Then what we're going to do to transpose that is that we read in the rows one at a time, and we use this interleaving operation to spread those rows out. And then we take multiple rows, and we spread each of them out, and then we interleave them. And then we just write that result back all at once. And that is the transposed result. Okay, so now this 8x8 transpose algorithm. Here is what Jay did. So I've got here a 16 by 24 matrix laid out like APL would print it. Jay's approach was to split this matrix into its 8x8 submatrices. And then we want to transpose it, put it over here. The idea is that you read one of these 8x8 submatrices. This just takes, because the row lengths are multiples of 8, all of these bytes here are aligned to bytes in memory. You can't just read a byte wherever you want. It has to be byte aligned. So you can read these 8 bytes just with 8 reads. And then you put them together into one register in memory. And then somehow you're going to transpose that 8x8 submatrix. I'll explain that on the next slide. And then you write it back to the result using, again, 8 writes of 1 byte. And the reason you can do that is because the row lengths, or the column lengths, were a multiple of 8. So in the transpose matrix, the row lengths are a multiple of 8. And you'll keep doing this. You'll go down the matrix by rows and columns, transposing each one. And then at the end, you can see you get the whole matrix transposed. So now, how do we transpose an 8x8 matrix. This is going to be done with a set of swapping operations when I take one big chunk of the matrix and I swap it with the other. So what I have up here is I've displayed the matrix both as an 8x8 matrix and as all laid out as 64 bits in a row. So I'm going to take this register, I'm going to copy it, I'm going to swap the top right and the bottom left corner. And now what happens is that the 4x4 submatrices of this matrix are now in order. So now all I need to do is transpose each of these submatrices. And so I'm going to do the same thing on each submatrix, but with 2x2 matrices. And then again. And now the matrix is transposed. There's actually, with this pdep instruction I mentioned earlier, there's another way to do the same thing, which is to, well, you can use the pdep to implement what's called a perfect shuffle, which is when you take all the bits in a register and sort of mix them together. So you'll split the register into two halves and spread each one out, inserting zeros between them, and combine them with a bitwise OR. So it's called a perfect shuffle because nobody shuffles like that. So it turns out if you do 3 perfect shuffles, that's equivalent to an 8x8 transpose. And there are actually 3 ways to think about that. The first is that a perfect shuffle is equivalent to multiplying by 2 mod 63, and a 8x8 transpose is equivalent to multiplying by 8 mod 63. Mod 63 because both the first and the last elements stay the same, so they both work like 0. So if you multiply by 2 3 times, it's the same as multiplying by 8. Or it's if you consider the perfect shuffle to be a 2x32 matrix transpose, you can think of an 8x8 matrix as a 2x2x2 matrix, and each transpose moves a 2 to the end. So doing it 3 times moves 3 length 2 axes to the end, which is like moving a length 8 axis to the end. And the third way to think about it is that it involves shuffling. So it is like a magic trick. That's our 8x8 transpose. So now the question is, if we have when the row length is not a multiple of 8, what do we do? So here I have again a something by 27 matrix laid out as APL would lay it out. But I don't really want to think of it like this because on the machine, the byte boundaries are all here. They're spread out through the matrix in this weird way. So instead, I'd like to align the rows so that all the byte boundaries are lined up. And then the rows just wrap around. So I'm going to draw the rest of the rows here. And now, in order to get an 8x8 submatrix to transpose, I need to pick out these bytes. And once I do that, I can do the same thing, just pull them out into a register and transpose, which we all understand by now. So now the task is to get these 8 bytes out. But once I do that, I'm going to just shift over 1 byte. It's important to notice that this is exactly the same shape, so I can do the same thing every time, and keep shifting over. So now the problem is to get these 8 bytes, but I can't actually read these directly. The best I can do is read these 16 bytes and then do some trick that I'll talk about to get them all in order. And then after that, I'm going to just read 8 new bytes to avoid reading 16 new bytes and discard the ones on the left and keep the ones that were on the right, and do the same trick and keep moving forward through the matrix like this. Now I need to know how to align rows. And this trick is Jay's more or less. He asked me if this might work, and I told him no. And then a few days later, I ended up implementing it. The idea is to split into odd and even rows, which actually makes the offsets much simpler. For the even rows, all the offsets have to be even. And if it's If in like in this case, our row length isn't a multiple of 2, then they have to be exactly 0, 2, 4, and 6 in some order. So we split that up, and now we find some way to get rid of the bits we don't want and align them all. And then we can just bitwise OR them together, and we end up with the 8x8 matrix in the order we wanted. So how do I... Now I've cut my problem exactly in half, and the question is, how do I align the even rows? So noticing that the offsets must be 0, 2, 4, and 6 in some order, what I can do is take the offsets that are 4 and 6 and shift those over by 4, and then take the offsets that are off by 2 and shift those over by 2, and now it's aligned. So I can't just shift part of a register, but what I've done by splitting into this is I've made what would be variable shifts into 2 constant shifts by the same amount. So the way I'm going to shift these bits of a register is to shift over the whole thing by 4, and take some bit masks to select the ones I want. So I want this piece of that register, and this piece from this register, and so on. And then I can combine these together, and you see that that has the bytes in the place that we wanted them, plus some junk. Now I do the same thing. I shift over by 2, and with a different set of masks, combine them. And now I use a mask to take away the bits that I don't want. That's all aligned. So that's the whole way. Actually, that's not how Dyalog does an 8x8 transpose. That's the other way that I didn't implement, which is simpler to explain. I showed when the row lengths are a multiple of 8, when the number of rows is a multiple of 8, and we work with the number of columns being a multiple of 8, and it's sort of backwards in that we read normally from the matrix, and then we transpose, and then we use this aligning technique. We add the transpose to a set of registers, and we use this aligning technique to get the bits that we want to write. So to summarize, we have when the number of columns is a multiple of 8, we use that method. When it's not, but the array is large, we just use an overtake. And actually, for small enough row lengths, this overtake uses the bit interleaving method I talked about, so it's important there as well. And then for these small row and column lengths, we do interleaves. And here's the performance of this solution. The obvious benefit is that version 16 looks a lot cooler. But so now I have to actually explain what's happening, don't I? So yeah, here again, this is a logarithmic graph. I've chosen a set of sizes that follow an exponential distribution, and then I've plotted the speed again in megabytes per second as a logarithmic graph. And so on the left here, for the vast majority of matrices, we are running maybe a little over 100 megabytes per second, and on the right, we're going from between something like 300 to 300 megabytes to 1 gigabyte a second. This is generally 4 to 20 times faster. There's a lot of variation. So on the left, you can see there's one matrix where we do really well. And this is J's technique. This graph is slightly unfair to J because just due to the way the links worked out, there's only 1 dot, and there should really be 4. And then on the right here, everything goes well. And these, here I'm transposing in by 1 matrices very quickly using just a copy on the memory. And so this works at, as I said, the maximum memory bandwidth of my machine, 11 gigabytes a second. Here, I'm not even doing anything. It works faster than that. And here, there are various different speeds in between. This one block is actually sort of a performance bug in 16. I I don't use this algorithm for that when maybe I should. And that'll be fixed in 16. You might think it's a lot of work for just this one small change, but actually it's only one character change in the source code, and it changes 1 pixel, so that all works out. All right, so there's transpose. I don't know that I have time for questions. Should I just stop there? Thank you, everybody.